Good morning, sir. My name is B. Ramu. I'm, f- I'm from third year ECE section from Institute of Aeronautical Engineering College. Today, I'm gonna give a presentation on the topic of phased array antenna calibration with probe positioning errors. The subject of microwave and radar engineering. Introduction to phased array antenna. The phased array antenna consists of multiple radiating elements that can be controlled to steer the beam direction electronically. They are widely used in applications such as radar communication and electronic warfare. Understanding their calibration is essential for achieving optimal performance and accuracy in signal transmission and reception. Basically, array antenna is, by naming itself, it suggests that the antennas are placed in array in the same phase. So this type of arrays can be called as phased array antennas. The importance of calibration ensures that the antenna array operates according to its designing specifications. It helps in minimizing measurements error and enhance the reliability of the system. Proper calibration can significantly impact that overall efficiency and effectiveness of phased array system. So I'm putting one picture how the calibration management is important, because improved accuracy and enhanced compliance, efficient workflow, cost savings. Because of these reasons, the calibration management is more important. A overview of probe positioning. Probe, pro, probe positioning is critical in the calibration process as it directly affects the accuracy and the measurements. Small errors in the probe placement can lead to significant disappearance in the antenna's performance. Understanding the typical positioning errors can help in developing strategies to mitigate their effects. Types of probe positioning errors. There are different positioning errors up there. Uh, Systematic errors, one of type of errors. It occurs consistently due to known biases in the calibration setup. Random errors. It arises from unpredictable factors such as environmental condition and human factors. And third one, misalignment errors. It can occur from the mechanical inaccuracies or improper setup procedures. Uh, to understand in easy way, I am putting one picture. Systematic errors versus random errors. Systematic errors, it uses structure measuring tape, and random error is timing dependence on reaction time. In systematic error, scale the always scale that always reads to high or low. Random errors, people take turns making readings. Systematic errors, reading an indicator from a poor angle. In random errors, rounding values up or down. Impact of positioning errors in calibration. Even minor probe positioning errors can lead to sustainable variations in the measured radiation patterns. These errors can affect the amplitude and phase of the signals received. Ultimately, Degrading performance, understanding the specific impact allows for targeted adjustment during the calibration process. There are different stages are there in calibration of positioning errors. First one is in call it as initial stage, and second one is robot teaching. Error modeling techniques. The error modeling involves quantifying the effects of probe positioning error on the calibration of outcomes. Techniques such as Monte Carlo simulations can be employed to predict potential measurements deviations. These models can guide engineers in identifying critical areas that requires more precise control. So in the picture I'm showing different techniques to build error modeling. Compensation techniques. The compensation techniques are essential to correct for known probe positioning errors during calibration. This method may include software algorithm that adjust the measured data based on error models. Active feedback system can also be utilized to continuously monitor and adjust positioning in real time. Compensation techniques, performance specifications for the closed loop system is stability, transient response, steady state response, TM or ESS. Trial and error approach to design. So these are some techniques. The flow graph is there, how the compensation will be done. Look at the picture, you can easily understand. Best practices for calibration. Regular maintenance and calibration of the probe positioning system can minimize errors over time. Implementing a robust quality control process ensure a high accuracy in probe placement. Training personnel on the importance of precise positioning can lead to improved calibration outcomes. Case studies and application. Real world case studies demonstrate the significant effects of probe positioning errors on antenna performance. Various applications such as military radar system and satellite communication highlights the need of precise calibration. Lessons learned from these cases can inform future calibration practices and technology development. So I conclude that accurate calibration of phased array antennas is critical for the successful deployment and operation. Ongoing research into advanced calibration techniques will help mitigate the effects of probe positioning errors. The future of phased array technology will depend on the continuous improvements in calibration methodologies. Thank you.